because this stuff's lagging behind that, isn't it? Right? An average star, that's going to take more than a second. Why? Because light travels 3 times 10 to the 8th meters per second, yeah? So it's going to take a bit more than a second for the star to go dark. Yeah? And if we could see the star, which, if we were far enough away, we wouldn't be able to, but if we could see it, it would go dark in the middle and dark at the edges later, because those runners are farther behind, yeah? Right? So our sun is too big unless it's pulsing in some very clever way, right? Like spectators at a sporting game, where they're, okay, do this, right? And now do this a little bit later, right? Or like the Chinese at the Olympics, right? It's like, holy cow, how'd they do that, right? Okay, unless they're doing something exceedingly clever, if the whole star is turning on and off, a variable star cannot create pulses shorter than a second. But these things are creating pulses really, really small, yeah? Right, so doesn't that mean the object from which they're coming has to be pretty small, right? There we go, right? So you can tell that by the size of these pulses. They're small, okay? So many things they could not be. The only thing small enough, rotating fast enough, according to what scientists knew, was a neutron star. So although you can't see it, so to answer your question, can we see a neutron star? No, but we can see radiation from something that has to be a neutron star. Nobody really questions this anymore. Yeah?
So how is she hearing?
Oh, it's just, they have speakers on it, so you can actually hear. They just take the radio signals and pretend it's a radio station, right? And maybe she wasn't hearing it, maybe she was just seeing them going by like this, right? Right. So here are 2 models. In the 1970s, they had 2 possible models, and I haven't gotten rid of this because it's kind of cool to see, a change, a gaining of knowledge, right? There was is it tangential, a beam of radio waves, or is it an off axis, right? There's a axis of spin and a magnetic axis. And the consensus, by the way, is now that it's this guy here, right? Real animations from the Hubble. Here's an animation. Let's look at the animation. Cannot open the specified file. Well, why don't you effing try? Okay. Sorry. It's like, are you clever enough to consult the registry? No, not really. Okay, so animation. I think this is the animation. So the Crab Nebula. I think that's where the 1987 supernova was that we saw. We now look at it. Of course, there's this pulsar there, right? They're zooming out now. Now you can see jets. So neutron stars spin up magnetic fields, and magnetic fields have jets, and they're just blasting off residual stuff like that, right? But just basically the reason why they're flashing is, we'll just hit play. The reason they flash is that it's like a lighthouse. It's shooting the radiation off at all times, but it's just flipping by us every time it spins by us. So it's like a flashlight, right? Lighthouse, yes I am, spinning all around. Quick flash here, quick flash there.
Will it ever stop pulsing?
Maybe, I don't know. Where is it? It's generating it because it's got spin, so it's generating electromagnetic waves because it must be consuming something, right? Using up energy, and so it might run out of energy eventually. I don't know. Seems like it's a thing that uses up energy, and so the answer would be possibly yes. But it might be something that doesn't. Okay, so here's an actual movie. This is great. They took the Hubble telescope and they took pictures days apart. Yes? And made a movie. And this is the Crab Nebula. And the thing that we're just watching here, we're supposed to be able to see like little jets. I don't really see them. Okay? But notice that you actually see this is the material surrounding. Here's the neutron star. This is material, and the magnetic field is churning that, right? So it's just like a little bread mixer, right? This is a crazy thing. So just watch. These are much faster than it really is happening, but you can see these. And then you're supposed to be jets there. I don't see them so much. So anyway, that's kind of cool.
They're heavy enough to have objects orbit them, right?
Yeah. We don't want to do the cosmological distance line. That looks grim. Pulsars, and then, now at this point, if we're...
So we don't
Say it again?
We don't talk about magnetars.
Magnetars, I don't know, we could talk about them. I'm not against, some people are against talking about them. I don't even know what it is. So.
It's just basically a neutron star with an insanely powerful
Magnetic field, yeah. And we're not going to really talk too much about black holes, spinning black holes and stuff like that. But that's all pretty cool. And then if it's bigger than, if it's less than two, I think the number we're seeing now when I look at stuff is about 3 solar masses. Okay, so it started out much bigger than the sun, right? 20 times or something, right? But if it's now is 2 or 3 times the mass of the sun, there's something called the neutron exclusion principle that props them up, that neutrons can't occupy the same space, right? Well, at 3 solar masses, it just don't matter, okay? Space itself is going to be collapsed, right? So it collapses even further, right? And it becomes an object, a black hole. And so the key concept here is that stars don't become black holes by getting more massive, right? Stars become black holes by getting small, right? The gravitational field strength, remember that the force is gm1, m2 over r squared, right? What happens is r gets small. Right? As the object gets small, the gravity on the surface of the planet gets huge, right? If you cut it in half, you get 4 times the gravitational force or field strength, right? At some point, light itself can't escape from the surface, and we'll look at that when we look at general relativity, right? Light's really fast, right? And then the curvature of space-time becomes infinite, and this is just a little problem because general relativity doesn't deal with infinity too well, right? So we don't have we can't use general relativity. And we don't yet have a quantum theory of gravity, right? So in the way quantum mechanics deals with infinity is that sometimes it's not infinite. It's just not, right? It's a probabilistic thing, right? So it can deal with that. We just don't have, and we are desperately trying to make a quantum theory of gravity. We just haven't detected a gravitational quanta of a graviton, right? A particle, a gravity particle, right? And then you can, all sorts of things about black holes, right? Black holes are surrounded by, if you've got a black hole, it's surrounded by something called an event horizon, right? And it could be quite close to the black hole itself, the singularity. I'll draw the little singularity. It's like, there it is, right? Okay. But there's a point of no return, right? And Stephen Hawking proposed that if you had a particle is just inside the event horizon, it just barely lacks the energy to escape if it's orbiting, right? Okay, and so if you have like a particle, a photon, or something like that that just can't, almost can escape, right? If its energy is uncertain, right, is on the order of what, h bar over 2 or something like that, right? If its energy is uncertain, it can actually escape from the event horizon. Then once it's gone, it's gone. Once it gets across there, it's gone. It gives the energy back to the universe, but it's already escaped, right? And so Hawking actually predicted that it's possible that a black hole could lose mass by Hawking radiation, right? And so although black holes are sometimes formed, if you had one that's just barely sub-Chandrasekhar, right? It's just barely, or not Chandrasekhar, but just below the whatever that limit is, right? Okay, it could possibly reemerge, come back into this part of the universe, right? And he said they looked for this type of radiation of a black hole, like coming back into the universe, right? And he says in his book, he says, it's a very sad thing that in 13 years they did not discover this, because if they had, I surely would have won the Nobel Prize. It's sad. That's what he's saying.
What did he say would come back as? Just like another
Yeah, it'll just come back as a neutron star. Just like, oh, there's a neutron star, right? But there would be a particular radiation signature that we would see, and they haven't seen it, And it might be that this is such a slow process that, it just hasn't happened, isn't likely to happen. Right? And the ways that we can detect black holes, by the way, is we can look at stars, right? And can't we, if we look at a star, we know how big it is. And if we look at it orbiting, we see a star going like around really fast around something we can't see. Well, gee, we can tell how massive that is, and if it's got a certain mass, it's got to be a black hole. It can't be anything else. There's nothing else it could be, right? So, do they exist? Well, they're hard to see, but you can extrapolate, right? In the center of the Andromeda galaxy, there's a dark object that's 30 to 70 million times the mass of the sun. It's got to be a black hole. In fact, they thought it was like just Andromeda, but every galaxy's got supermassive black holes, as Muse would say, right? In the centers of them, right? Supermassive black hole.
They also get various forms of radiation,
Yeah, like X-rays and